Before I run WEPP, I will go back to the options and I will check the Run Flow Paths box so we can also look at the flow path results. Remember that when you run this option, the model will take a longer time to complete, so only run it for smaller watersheds and for a small number of years. In our case, we are running a simulation with 20 years of climate, but the watershed is relatively small, so we should not wait too long. After clicking on the Run WEPP button, you will see several notifications in the status bar, which tells you what the model is doing: preparing hill slopes, running flow paths, preparing watershed, running watershed, building total wattset.txt file, etc. The time it takes the model to complete will depend on the size of your watershed. As long as you see the status bar updating, it means that the model is performing the different tasks. For larger watersheds, though, it can happen that the model gets stuck on displaying a certain task, usually somewhere close to the end of the run, although the run is completed. In this case, you can check the run log to see if the run is complete. You can find this log in the runs folder in the Power User panel. And here look for calculating channel streamflow measures done. If this message is displayed in the run log, then go back to the run and simply refresh the page. In our case, the model hasn't reached the end of the simulation, so we will go back and wait for the model to finish. Smaller runs should only take a few minutes to complete, but for larger watersheds, you could end up waiting 20 or 30 minutes. You should not have to wait for a run for more than 1 or 2 hours. If you do end up getting stuck in a run, send us the URL of the run so we can debug it. When the model run is ready, you will see the message "Fetching Summary Success" in the status bar. Now you are ready to view the results. And let's start with the watershed loss summary. Once you open this document, at the top of the page, you can see a summary of the results at the watershed outlet. Specifically, you can see the total contributing area, precipitation and stream discharge both in meters cubed per second and in millimeters per year, total hill slope soil loss, total channel soil loss, and sediment discharge at the watershed outlet, both in tons per year and tons per hectare per year. And you can also see the sediment delivery ratio for the watershed. Below this, you can find the average annual summary for each hill slope and channel for the 20 years of simulation. Here we have the WEPP ID and Topaz ID. These are hill slope identifications used either by the WEPP model or by Topaz, which is the other model we are using to delineate the watersheds. We usually display both of these numbers because if you run the WEPP model, all the input files are ordered by the WEPP ID. But if you look at the spatial results, such as the shape files, or if you look at the map in WEPPcloud, the hill slopes are labeled according to the Topaz ID. Next in the table, you can find the land use and soils codes, slope length and area, runoff, lateral flow and base flow, soil loss, deposition, and sediment yield. The soil loss is a sediment that eroded from this particular hill slope, while the sediment yield is the soil loss minus sediment that got deposited along the hill slope. In this case, soil loss and sediment yield are similar, but most of the times you want to look at the sediment yield column, as this is what leaves the soil profile. You get a similar type of information by channel, except here you have both a channel area and a contributing channel area, and also you have sediment yield and channel erosion. To understand the difference between these variables, let's look at the example watershed from the main page of the WEPP user manual. Here we have a watershed with 5 hill slopes and 2 channels. Hill slopes 1, 2, and 3 drain in channel 1, and hill slopes 4 and 5 drain in channel 2. The channel erosion is calculated based on the channel area of each of these channels. So channel erosion is only the soil loss from the area of these channels. Now, sediment yield, on the other hand, is whatever gets delivered at the outlet of a particular channel and is based on all the sediment that is delivered to that channel from the surrounding hill slopes and the channel erosion from that particular channel. For example, the sediment yield at the outlet of channel 2 is equal to the sediment yield delivered from channel 1, which contains soil loss from hill slopes 1, 2, and 3, and the channel erosion from channel 1, plus the sediment yield delivered from hill slopes 4 and 5, and the channel erosion from channel 2. Therefore, the contributing channel area is the area of all the hill slopes that drain into a particular channel, plus the area of that channel, which means that the contributing area at the last channel of a watershed is equal to the area of the watershed. If we scroll all the way down, we see that for the last channel, the sediment yield is 3,700 tons, and the contributing area is 530 hectares. This is the same as the total sediment discharge at the watershed outlet and the total contributing area to the watershed outlet. The next result is the return periods report. First at the top, you'll see the equation used to perform these calculations, and then you'll find the return period analysis by parameters. And how would you interpret these results? Let's look at the peak discharge. Here you have recurrence interval, a date, and a peak discharge. Remember, we ran the simulation for 20 years, so the maximum recurrence interval is 10 years, which is the equivalent of a 10% annual exceedance probability. 5 years equals to a 20% annual exceedance probability, and a 2-year recurrence interval equals to a 50% annual exceedance probability. So every 2 years, you have a 50% chance of observing a peak discharge, for example, of 7.8 cubic meters per second. And every 10 years, you have a 10% probability of observing a peak discharge of 24 cubic meters per second. You can find these calculations for other variables, such as precipitation, runoff, 10 or 30 minutes peak rainfall intensity, and for the sediment yield. You'll also see here an option to show extraneous parameters in the tables. If we look at the precipitation, for example, a precipitation event of 280 millimeters has a recurrence interval of 10 years. This particular event happened in January, in year 15 of the simulation, and the event produced 7.4 millimeters of runoff, a peak discharge of 0.45 cubic meters per second, and a 0.21 tons of sediment. All these other extraneous parameters might not be important, but sometimes it's useful to check them if you want to better understand the results. For example, it might be useful to know if a certain event happened in the summer or in the winter. At the bottom of this page, we have an additional resource with a culvert diameter size estimator spreadsheet, which is courtesy of Dr. Bill Elliott. If you open it, you'll see an equation that allows you to estimate the culvert diameter for a given flow rate, which you can calculate based on the peak discharge from the WEPP model. The sediment characteristics report contains information of the particle size from both the channels and the hill slopes. For example, the sediment particles from class 1 have a diameter of 0.002 millimeters, and they contain 100% clay particles and 43% organic matter. Class 2 contains 100% silts, class 5, 100% sands, and classes 3 and 4 contain a mixture of sand, silt, and clays and organic matter. And then if we look at the sediment distribution by class, class 1, which is all clays, is 3.2%. Class 2, which are the silts, is 17.3%. Class 5, which is comprised of sands, is 26.9%. And the rest are aggregate classes. And lastly, we're calculating a distribution of all the clays, silts, and sands from the primary sediment classes and the aggregates. So out of 3,700 tons of sediment per year at the watershed outlet, 51.6 of those aggregates are sand and 10.8% are clays. And similarly, you can find this information for the hill slopes. I talked about the run log earlier, so let's now look at the watershed balance reports. The first report provides you with the information on precipitation, surface runoff, lateral flow, ET and percolation by hill slope, and the second report provides the same information by year, and it also displays an additional column with the total sediment by year. Lastly, the daily graph shows daily annual runoff, lateral flow, and base flow. With the lower bar, you can zoom in to better visualize the results from a specific year. Another way to look at the results is to look at them on the map. So go all the way up to the map, deselect the labels, and then select the pie. Now you can display the results on the map. And here we have the runoff. You can move the bar to the left or right to change the maximum values. Similarly, you can display lateral flow and base flow. Now you can use the magnifying glass and click on an individual hill slope to find more information on the hill slope ID, width, length, dominant land use, and the dominant soil. You can also view the sediment deposition or loss by hill slope, where the negative values are areas of deposition and the positive values are areas of erosion. In this case, we don't have deposition, so we're not displaying any of the negative values. When you run the model with the flow path option checked, like we did for this run, then you can also look at the results by pixels. Now, within some hill slopes, you can see the areas that are producing more erosion. For the advanced users that are familiar with the model inputs and outputs, you can find these in the runs and the outputs folders. Here you have many of the model inputs by hill slope and watershed, and you can find the results by hill slope and at the watershed outlet. I'm showing you where you can find these files, but I'll not talk about them in this video as it can get quite complicated. But here are all the model inputs and outputs for those of you that have more in-depth understanding of the model. The last thing I want to show you is the model sensitivity to some of the options we have on the interface. Here I have the results for the same watershed we just looked at, but ran with different options. I'm altering the critical source area and the minimum channel length. I'm clipping the slopes to 300 meters when I'm using larger critical source area and minimum channel length values. I'm using both the closest climate and a climate based on the multi-factor ranking, and I'm using one single climate for the watershed and one single climate per hill slope. See that the precipitation amount and even the total runoff doesn't vary much, but we do have large differences in hill slope sediment yield. So for the same watershed, we can predict sediment yield from 1,900 tons or 3.7 tons per hectare to 4,700 tons or 8.6 tons per hectare. These are quite different results, especially for such a small watershed. But I'm showing this to you because I want to stress out the importance of choosing the right climate when running your simulations, and also to emphasize that you should always interpret the results in relative rather than absolute terms. Especially for climates, we have put a lot of effort in incorporating the best available national weather data sets, but some of these data sets might work great in some regions, while they can under or over predict the precipitation and temperature in other regions. So instead of looking at the absolute numbers from the model results, we recommend you to look at the results in relative terms. For example, you could run a watershed with undisturbed and disturbed conditions and calculate % increase in sediment due to the disturbance. Also, you can use the model to identify areas within your watershed that are more sensitive to erosion. For example, you can identify specific hill slopes, elevations, soil types that are more likely to cause an increase in erosion, but you should not necessarily use the numbers as ultimate truths. We are constantly improving the model, and we are incorporating either new data sets or new routines to better represent certain processes in the model, but we will rarely truly capture the full variability in runoff and soil erosion across various landscapes or disturbances. So we want you to be aware of these issues when interpreting the results. This is all on running the interface and interpreting the results. We will have another short video after this on how to run multiple management scenarios and duplicating a watershed.